Let's evaluate some 3D limits. Now remember that when we think about the way limits are constructed, we say that the limit of a vector valued function is equal to some numerical vector if each of the individual components approach those values. So what does that mean? That means that essentially to take the limit of a vector valued function, we take the limit of each individual component, and if those limits exist and are real, we say that it converges to this vector, to some vector. So let's take a look. So if we have the limit of t as t approaches 2 of this vector, well, I'll just try to plug it in. So I say, well, when t equals 2, that equals 6. Now when t equals 2, that's 2 over 4 minus 1. So that's 6i plus 2/3 j. And when t equals 2, 1/2 k. Simple enough. Now for the next one, I say that t equals 1. Well, I can plug that in here, and I'll get that's the square root of 1, so that works. But if I come over here, natural log of 1 is 0. But 1 squared minus 1 is also 0. So I have a 0 over 0 case. As you remember, that's an indeterminate form. So let's skip that and see if we even have to care. So if I look over here, what I see is if I plug in 1, I get 1 over 0. Now, in the three-dimensional case, if I have like a real number here and an infinite number there, that doesn't really make sense. So what we would say is that this limit does not exist, or DNE. So we didn't even have to consider that piece. So that's kind of nice. So don't work any harder than you have to here. If you can find where it blows up somewhere, then just keep on going. Now, for this one, the limit as t approaches 0. That right there looks like a 0. So that's 0i. That looks like a 0. That's 0j. But over here, I have 1 minus cosine of 0. So that's 1 minus 1. So that's 0 on top. But I have a 0 on bottom. Well, that's a problem. So I have that limit. Now, if you remember, when you have some sort of 0 over 0, which is an indeterminate form, you can do a couple of different things. But probably the easiest and most straightforward is L'Hopital's rule, which says that if these evaluate to either 0 over 0 or infinity over infinity, and they're both differentiable functions, then this limit is the limit of their derivatives. So 1 derives to 0, negative cosine derives to positive sine of t derives to 1, sine of 0 is 0. So at the end of the day, we end up with a 0 vector. This vector approaches, as t goes to 0, that vector approaches the null vector, 0 vector. Now, that's the end of this piece. If you don't care anymore, that's fine. You've had your examples. But I do want to show you one other piece if you're interested. So in computer programming, this right here is difficult to deal with. What happens is when you have small numbers and you're trying to evaluate limits or some sort of function numerically, this thing explodes because with round off error in computers, you can end up with, even though this thing shrinks down to 0, the way that the numbers may round off, you may end up with a really small number divided by, another equally small number, but the numbers can go wonky. I don't know if you've messed much with floating point numbers in computers, but they're not perfect. They're not continuous. So these small errors can accumulate. So something that you can do to mitigate that is have rules in place. Use trigonometric properties so that you can always represent certain practices. So, for instance, I'm going to use something more like pseudocode or Python in computer programming to say, what you can have is some sort of condition that says if t is less than some sort of small number. So let's say that we call some sort of epsilon. And in this case, we'll say that epsilon is really close to like, something like 10 to the negative fifth. So if t is less than some epsilon, if your function is something like a sine of t over t, then that function, we're going to assign it to equal to 1. Now you may ask yourself, what does that have to do with this particular function? Well, what we have is 1 minus, here I'll do it in a different color. What we have is something like 1 minus cosine of t over t. But we can use those trigonometric identities to multiply by 1 plus cosine of t, which then gets us 1 minus cosine squared t over t, 1 plus cosine of t, which then reduces to sine squared t over t times 1 plus cosine t, which then we can split into sine of t over t times sine of t over 1 plus cosine of t. So why does that matter? Well, the reason being is if you represent this function in this particular way, and maybe you have some sort of switching mechanism that says if the value is really low, call the function like this. If the value is really high, don't. Because this is going to be more expensive from a computer standpoint. Well, what you'll find is that since this is really close to 1 if t is close to 0, you can have some sort of function that says, if I have some sort of limit valve that takes in a value of t, I can say if t is less than, again, some sort of epsilon, then I can return this value. And it's because this is what's called, it's called numerically stable. Because cosine for low values approaches 1, so this approaches a half, and this is close to 0. So since this number and this number are not very close to each other, numerical stability is not a problem. Otherwise, you would return this. Really, you need to say something like if the absolute value of t is really close there. But the idea here is that we can use the mathematics here to inform how we instruct computers to handle things so that their problems aren't our problems. This is a bit overkill for doing these types of things, but in real world scenarios, these things do come up. Floating point issues can cause significant problems if you don't handle them very well.